and welcome to tonight's News at 8. In tonight's programme, as part of this week's focus on the global energy surge, we will be looking into the rapidly developing wind energy industry. Before this, however, our correspondent Ryan will give us a brief introduction into this fascinating field. Over to you, Ryan.
The harnessing of energy from wind has a long and varied history. The earliest forms of this come in the use of sails for boats, as well as windmills to drive mills used for processing agricultural produce. The first wind turbine used to generate electricity was built in 1887 by Scottish professor James Blythe of Strathclyde University, who used the device to power his own home. By 1927, the first business producing wind turbines for commercial use had been opened in the US. And continued development in the technology led to the opening of the first offshore wind farm in the UK in North Wales in 2003. And the UK is set to possess the largest offshore wind farm in the world at Hornsey by 2022. According to a recent forecast by the International Energy Agency, the next 2 decades may see investment in offshore wind to total $840 billion globally. And thus, in view of the current government objective to cut almost all emissions in the UK by 2050, the importance of the cleanest and most cost-effective mode of energy generation currently known is only set to grow.
Thank you for that informative piece, as always, Ryan. As Ryan mentioned, this is an area with high predicted growth in the future. With this in mind, we have been given exclusive access to the new design of Gener-8, a leading wind turbine engineering firm who are playing a key role in meeting the surge in demand of renewable energy around the world. We are now joined on the line by Gener-8's chief aerodynamicist, Isaac Santos, from their offices in London. Good evening, Isaac. Thank you for joining us.
The pleasure is all mine.
From what I understand, there were some key design limitations for this design. Could you please tell me a bit more about these?
So the turbine must have a maximum diameter of 45 centimeters, withstand wind speeds of up to 12 meters per second, and in terms of rotation speed, it must not exceed 3,000 RPM. It must also have an optimum TSR, which is basically the rotation speed that gives maximum power, between 3 and 9. In terms of design, we had to decide on the number of blades, as well as along each section of the blade, what the chord and twist angle would be.
That certainly sounds challenging. How are these limitations resolved?
Well, we first chose to optimize for the largest diameter and the largest wind speed, as that ensures maximum power can be obtained from the wind. We decided to go for a 3-bladed design, ensuring that each blade sees a smaller force and as a result deflects less, which makes our assumptions of no blade deflection much more accurate. We then used a blade element momentum code to, for each TSR, find the optimal chord and twist. We then chose the TSR that gave us the maximum power. The optimal twist was found by setting the angle of each section such that it gives maximum leftover drag. And the optimal chord was found using the Schmidt's formula, which we found to be the most accurate and reliable formula for this application.
It's incredible how much work went into the design of this turbine. Do you think that noise pollution presently is a problem for wind turbines?
Well, obviously it's not that big of an issue.
I'll have to answer your question, but I'm afraid I simply cannot hear you. They're this noisy when they're standing still. God knows how loud they can actually get.
Apologies about that technical interruption. Please continue, Isaac.
As I was saying, noise is a critical issue that Gener-8 have been doing much research on. In fact, in the current design, we decided to reduce noise by cutting the airfoil's trailing edge at 90% chord, which has been shown and proven to reduce noise while having a minuscule effect on the aerodynamics and power.
Once the conceptual stage of design was completed, what was the next stage?
Once we had a fixed design, we cross-checked with external sources and programs. We made use of QBlade, a turbine design program, to predict the power and TSR for the turbine, which gave results very close to our in-house code.
Thank you very much for your time, Isaac, and for giving us a much clearer understanding of the challenges and considerations in designing a wind turbine. Following on from Gener-8's chief aerodynamicist, Isaac, we now have a special report from Gener-8's principal structural engineer, Harrison Moss.
It does not take long to see the extent to which wind turbines exist in our current landscape. Just a short journey out into Britain's countryside can display this. Focusing on the blade only, its structure can be optimised following the aerodynamic optimisation in order to ensure peak power output. This is completed by discretising the blades into thousands of thin elements, and for all of the further out elements, summing the moments generated by their aerodynamic forces in order to find the resultant moment on the cross-section we are focused on. Using engineers' theory of bending, we can take the resultant moment and find the peak stress acting at some location on the cross-section. The volume and therefore mass of all elements further out can also be obtained, and then using radial acceleration we know the force acting on that cross-section. Summing the peak stress caused by the resultant moment as well as the centripetal force, we can find the peak stress acting on a particular cross-section. Using a plot of span versus peak stress, we can then ensure that the blade will not fail due to a material failure. Then, knowing the moments acting on each cross-section, we can additionally find the second moment of area for each cross-section. Using these two values, we can calculate the radius of curvature and therefore the displacement along the blade. We can compare this value obtained against other FEA simulations and get incredibly similar results. It is clear that as we want to build larger and larger turbines for greater power outputs, their structures will become more important than ever.
Thank you for preparing such an informative piece, Harrison. Having spoken to two of the key engineers for the design of the wind turbine, Hayley, our manufacturing correspondent, has been given exclusive access to the factory where the design comes to life.
I'm here with the owner of Gener-8 Industries. I've been granted an exclusive look into the design of this never-seen-before wind turbine. Thank you very much. Will you tell us a bit about the steps to making this turbine? Sure. Here we see the centre part of the turbine, known as the hub, being created in computer-aided design before it is sent to the machine. I know the tolerance of the part has to be within 0.25 millimeters. Is that fulfilled? Of course. What do you take us for? We here make sure all our parts are made to the highest standard. Look, here is one of our technicians precisely measuring the part. As you can see, our part deviates from the specification by only around 0.05 millimeters, completely in range of the tolerance. And how are the blades made? The blades and nose cones are printed using a state-of-the-art 3D printer. Taking into consideration of transportation and manufacturing constraints, the 3D printed part has been limited to fit in a box of 400 by 150 by 100 millimeters. This is done by adding hinges to the nose cone so the turbine can be folded. The placement of the hinges is so that we can align the fiber to the print direction for maximum structural strength. And why have you chosen 3D printing as opposed to other types of manufacturing? This is a form of rapid prototyping. We want to efficiently test the CAD sent to us by Gener-8 with minimum cost. We then glued the turbine. Wait, glued? Yes, glued. After unfolding and gluing, we sanded the hinges down for lower skin friction and also added acetone finishing on the surface for the same reason. What's the shape of that nose cone? It is the solid revolution of an elliptical equation. The shape is chosen because it is good for subsonic speed. We want the nose cone to minimize aerodynamic drag so the flow loses a minimum amount of energy before reaching the blades. I also noticed the back of the blades are a bit blunt. Why is that? This is done according to the noise reduction design specification given to us by the aerodynamicist of Gener-8. Thank you very much for giving us a look into the manufacturing process of Gener-8 Industries. Back to Isabel.
Thank you for that report, Hayley. It now seems only fitting that our independent scientific expert, Christian, evaluates the design of Gener-8 and the challenges that scaling up this design can have.
Yes, hi Isabel. What we can see here is a design with many important elements executed well. However, there are still a number of aspects to address, such as the fact that to scale this technology up, many turbines must be placed out in open areas that the question of turbulence in the leading turbine's wake inhibiting the potential of the rest of the turbines in the field. This is something that certainly must be optimized. Of course, improvements in blade geometry may help with the turbulence generated, but this will have to be coupled with wind farm design. Lastly, it is interesting to note that the engineers decided against no stippling in the end due to complexity in calculating the optimal placement of dimples given the deadline of the project. Perhaps for their second generation model, this is a technology they could be able to harness to their benefit.
That's all for tonight's programme. From the team and I, good night.